Right, so AS differentiation. Question 1. So the first one is the most straightforward one. Each term is clearly separate from the others, so we can just work through differentiating each in turn. So dy dx will be 4x cubed plus 2 minus 9x squared. So that's nice and straightforward. There are 2 marks for that. A method mark where I would be looking that you were doing the right thing, which is dropping the power down and then subtracting 1 from the new power, and then your answer or accuracy mark for getting the 3 correct terms. Part 2. Y equals 3 plus 2x all over the square root of x. Okay, well, we need to get rid of that square root and turn it into index form. And in AS, in order to be able to differentiate that, you need to be able to separate those terms and have 3 or have separate terms like in that first one. So square root is the power of a half. If I want to bring that from the bottom up, then it would change to minus a half. So I would have x to the minus a half multiplied by 3 plus 2x. Now I could multiply out that bracket, and I would have 3x to the minus a half, which I can differentiate, plus 2, and then here I'm going to have x to the 1 times x to the minus a half. So let's write that so that you can see it. That's to the power of 1, that's to the power of minus a half, and using your sort of GCSE indice laws, if the bases are the same, you can add their powers. So we have 3x to the minus a half plus 2x to the 1 plus minus a half, which will be to the power of a half. Now we're in a position where we can differentiate. So dy dx will be minus a half brought down, so minus 3 over 2 x, and then we would be subtracting 1 from that, so that would be from minus a half to minus 1.5, which is minus 3 over 2, plus I'm going to bring that half down, it'll cancel with that, and I'll just be left with minus a half minus 1. So that's what they're looking for, and the marks for that would be a B mark. I'm looking for you to get something that can be differentiated, and then the method mark is for showing me you are differentiating, and your accuracy mark for actually getting the job done. Part 3. Y equals x minus 2, 2x plus 1 all over x to the 4. So it's a similar situation we have here. First of all, let's expand the bracket on the top. So I have 2x squared plus x minus 4x is minus 3x minus 2 all over x to the 4, but I can write that x to the 4 as x to the minus 4, which I can then multiply in. So when I multiply in, I'm going to add the powers, so 2 minus 4 is minus 2, then minus 3, that's x to the power of 1, times x to the minus 4 is going to give me x to the minus 3 minus 2 x to the minus 4. Now it's in a format that I can differentiate. So dy dx will be minus 4 x to the minus 3 plus 9 x to the minus 4 plus 8 x to the minus 5. 3 marks for that. Same situation as the one above. There's a B mark. I'm looking for you to manipulate the expression to put it in a form you can differentiate, and then a method for doing some correct differentiation, and your accuracy mark or your answer mark for getting them all right. So the total marks for question 1, 8. Question 2. Given that x equals 3u plus 2, u squared minus 3, find the second derivative. Okay, so same as the previous question. First of all, I've got to get that in the form I can differentiate. 3u cubed minus 9u plus 2u squared minus 6. So I can differentiate that. dx du in this case, I'm differentiating x with respect to u. 9u squared minus 9 plus 4u. 6 goes because it's a constant. I then need to differentiate that a second time. 18u, 9 goes because it's constant, plus 4. Job done. 3 marks. 1 mark for getting it in the format you can differentiate. 1 mark for differentiating once correctly. 1 mark for differentiating the second time. So 3 marks available for that question. Question 3. Now this is much closer to the sort of question we'll be tackling in year 13 in A2. The curve has an equation 2x cubed minus 3x squared minus 8x plus 9. Find the equation of the tangent to the curve at the point P where with the coordinates 2, minus 3. So I'm looking for equation of a tangent, so I'm looking for an equation of a line. The line passes through that particular point. I need a gradient value. The gradient value is what is generated from the gradient function, which is the derivative of that. So to find the gradient, I need to first of all differentiate. This time I'm differentiating y with respect to x. 6x squared minus 6x minus 8. So the gradient at P2 minus 3 will be 6 x coordinate 2 minus 6 x coordinate 2 minus 8 equals 24 minus 12 minus 8, which is 4. So now for the equation of the tangent, okay, so EQ little n of tangent, we're going to use y minus y1 equals mx minus x1. So at P, x1 is 2, y1 is negative 3, gradient is 4. Y minus 3 equals 4x minus 2. Y plus 3 equals 4x minus 8. Simplify that a little bit further. Y equals 4x, bring the plus 3, becomes a minus 8 minus 3 is minus 11. So the equation of the tangent is minus 11. And then part 2, so that's part 1. Find the coordinates of the point Q at which the tangent is parallel to the tangent at P. So if it's parallel, it's going to have the same gradient. So at Q, tangent is parallel to tangent at P. M equals 4. You can't see that, it's off the screen, sorry. So at Q, the tangent is parallel to the tangent at P, so M is 4. So I can now use that information in my gradient function to find the x coordinates where the gradient is going to be 4. So in 1, 6x squared minus 6x minus 8 equals 4. 6x squared minus 6, 8 minus 12 equals 0. Now you can divide through it by 6 and you can factorize that, all lovely. But remember that we've got our funky calculators which has got a quadratic solver. So let's just do that so I can remind you where it is. So menu, move down to the xy equals 0, press equals. It's not a simultaneous equation, it's a polynomial and it's a quadratic, so the degree is 2. 6x squared negative 6, remember you have to press the negative, not the take away, and negative 12 gives you either x equals 2, which we already know is P, or x equals negative 1. So that, hang on, it's off the page as well. So that means that Q has got an x coordinate of minus 1. And now I can plonk that into the equation of the curve to find y. So, damn. So I should have called that equation 1, that equation 2, that equation 2, and now plonk it into 1. So in 1, y equals 2 minus 1 cubed minus 3 minus 1 squared minus 8 minus 1 plus 9 equals minus 2. That's going to be plus times a minus is minus 3 plus 8 plus 9. So I've got 17 take away 5 equals 12. Therefore Q has got the coordinates minus 1, 12. Okay, so let's dish out some marks for that one. You're going to get 1 mark if I see the correct gradient of 4. You're going to get a method mark if you've correctly substituted into the coordinate equation for the line, and you're going to get an answer mark for 4x minus 7, or however you've rearranged that. Then there's going to be a method mark for equating the gradient with a gradient function to find the coordinates with that gradient, and an answer mark for factorizing it and getting the x coordinate at q of minus 1, and then an answer mark for the y coordinate that corresponds. So the total marks for that question is 6. And then, hang on, question 4, use differentiation from first principles, and this is where you were all groaning, to show that the derivative of x cubed is x squared. Okay, so we let f(x) be x cubed. The formula starts off with, rather than dy's and dx, is deltas, which indicate a small shift. And it's the limit as delta x tends to 0 of f of x plus delta x minus f of x all over delta x. So f of x plus delta x, if we work out that first of all, in our case is going to be x plus delta x all cubed, which is x plus delta x times x plus delta x squared, which is x plus delta x times x squared plus 2x delta x plus delta x all squared. So just expanding out that bracket. When you're squaring, you can either write it out a second time, or it's the first one squared, the last one squared, and the centre is double the product of the two, so 2 lots of x delta x. Now I have to expand that out, so this term by everything is going to be x cubed plus 2x squared delta x plus x delta x all squared plus x squared delta x, which is that times that, then plus 2x delta x squared plus delta x cubed. Okay, let's see if we can tidy this up a little bit. So x cubed, and I've got x squared delta x terms and another x squared delta x, so 3x squared delta x. So I dealt with that one, x delta x squared plus 2x delta x squared is 3x delta x squared, and then plus delta x cubed at the end. So that's what that is. So back into this. So we say in 1, delta y over delta x at the limit where delta x tends to 0 is that 3x delta x all squared plus delta x cubed minus fx minus x cubed all over delta x. So the x cubes cancel. So they've gone. And I can write this, just like I was doing with the other fractions, as delta x to the minus 1 times 3x squared delta x plus 3x delta x all squared plus delta x cubed. When I multiply that in, That and that are going to become 0 because that's the power of 1, so they become to 0. So the next line, delta y delta x, is the limit as delta x tends to 0 of 3x squared. This one is going to be 3x delta x because it's going to be 2 minus 1, and this one will become delta x squared. So I've got rid of that fraction. Once I've done that, now I can say at the limit where delta x tends to 0, delta y delta x, delta y delta x tends to dy dx. So dy dx will be 3x squared. As delta x pushes closer and closer to 0, that term and that term also go to 0. So 3x delta x tends to 0 and delta x squared tends to 0 because that is getting closer and closer to 0. The multiple of it will be, and so will that. So at that limit, we end up with the differential that we know is 3x squared. So as I said in class, that isn't something that's examined in A2. It's a standalone AS thing, so don't lose sleep over it. But I do want on occasion to show you proofs of certain things, and that's how we'll be doing it from first principles. So the marks for that, 4 marks. You're going to have M1 for correctly substituting into the standard first principles equation, and A1 or B1 if you substituted in everything right. Sorry, no, shut up, Jones. For correctly expanding the cubic is what your B1 is for. So correctly expanding the cubic is B1. M1 is for putting it into the formula. A1 is for getting it to the point where we've eliminated the delta x fraction, and then A1 is for the blurb about everything tending to 0 and ending up with the 3x squared. Good fun.